And we're going to start out with talking about different ways of measuring concentration. We talked about concentration a little bit before in terms of molarity. We'll talk about a few different ways that we can consider and talk about concentration that come in to play in different contexts. So concentration, so obviously solutions have variable concentration. You can have a stable homogeneous solution of water and sodium chloride at various ranges of sodium chloride. So it's not enough to just say, I've got an aqueous solution of sodium chloride. You have to specify how much sodium chloride there is. So to describe a solution, you need to describe the components and their relative amounts. In a solution of aqueous solution of sodium chloride, you got sodium chloride and you got water. And so the terms dilute and concentrated can be used as qualitative descriptions of the amount of solute in solution, but that's not really good for solving problems, right? What does dilute mean? It's sort of in the eye of the beholder. So you want to be able to express the actual numbers. Concentration is essentially the amount of solute in a given amount of solution. Occasionally per amount solvent in some cases. So concentration units, there's a bunch of different concentration units. The most common one we've seen is molarity, in which it's the amount solute in moles divided by the volume of the solution in liters. And the reason we use that, a lot of cases, if you're doing stoichiometry, it's really easy to work with because then we can measure volume of the solute by just measuring in a beaker. So molality is another concentration definition that comes up. It's amount of solute in moles, again, and divided by mass solvent in kilograms. And this is usually used in cases where you have large changes of temperature. The volume of a solution will change with temperature, right? Because density changes with temperature, but the mass will not change with temperature. So if you have properties that you're looking at that where you're going to be looking at changes in temperature, molality can be more convenient to report things because you don't have to keep figuring out what the volume of the container is. Mole fraction occurs in several equations. So the mole fraction is the amount of solute in moles divided by the total amount of moles in the solution. So here we're literally looking at numbers of molecules. And that occurs in a lot of equations. Of course, you can't really measure the number of moles. You'd have to take the volume and extract the moles from that. So, or when you start a solution, just measure out exactly the number of moles you want of each. But it occurs in a lot of equations, and so it can be very useful. There's no units there, right? Because it's a pure number over a pure number. So it's 50% one thing versus the other thing. Mole percent, it's really just the same thing as mole fraction, except expressed as a percent, right? So that's pretty straightforward. Parts by mass. And so sometimes, especially in like environmental engineering, when you're dealing with low concentrations of things, you'll talk about the parts by mass, such as the mass solute, and this will be parts by mass, will be mass of a solute over the mass of the solution. You could also have parts by volume, with the volume solvent over the volume solution. Which is the one that's reported really depends mostly on what the convenience is for that particular application. So yeah, most common solution concentration measure, molarity, moles of solvent per 1 liter solution, describes how many molecules of solute in each liter of solution. Again, this I probably don't need to belabor this much, but it's very useful in terms of measuring out specific moles of solution by just using a beaker. Yep, so we can keep on going there. Molality is a little less common, but it still is useful in some applications. And it's moles of solute per kilogram of solvent. And this is the key, it's per kilogram of solvent, not per kilogram of solution. Yeah, so otherwise, but does not vary with temperature, which is very useful for applications when you're making measurements as a function of temperature, right? Because it's based on masses, not on volumes. So the molality is usually indicated by a lowercase m as opposed to a capital M for molarity. Express the concentration of aqueous 2.0 molar H2SO4 in molality. Okay, well, it's going to be mole solute. So let's say we have 1 liter, right? Might as well pick we're given a concentration, so we can pick an arbitrary amount. So if we take 1 liter solution times 2.0 moles H2SO4 per liter, then obviously we're going to get 2 moles H2SO4. All right, so the question is, what is the mass of the solvent in 1 liter solution? So we actually don't have quite enough information to solve this here. We could make an approximation, a reasonable approximation. 2.0 molar, it's not super dilute, it's a little concentrated, but we could assume that in 1 liter solution, we had 1 liter H2O, because maybe the salt dissolves, the salt of the sulfate ion is not taking that much space because the water can pack around it, in which case that would be 1 kilogram solvent. Now, it's probably a little less than that. So let's go through and carry out the calculation and then do some corrections at the end. So in this case, it'd be pretty straightforward. It would actually be 2.0 molal as well, right? Because there's 2.0 moles solute, and there's approximately 1 kilogram solvent. So it'd be about, 2.0 molal. Now the question is it higher or lower than that? Well, if there's 1 liter solution and there's some H2SO4, there's probably less than 1 liter of just water put into that. And so there's going to be a little less than 1 kilogram solvent. How much less? Well, maybe you could go by moles, and so there's 2 moles H2SO4. Rule of thumb, there's about 55 moles of water in a liter. So maybe there's only, instead of being 55 moles per liter, there's only 53 moles per liter. So that's about 1 kilogram solvent times 0.96, that'd be about 0.96 kilograms. And so that would give us a 2.0 mole solute divided by 0.96, which would give us 2.08 molal. So it's almost certainly, we know that it's going to be a higher molality than molarity. How much higher? Well, probably not that much, maybe up to 2.1 or so. So it's still in the reasonable range. So if you have dilute solutions, dilute aqueous solutions, the molality and the molarity are relatively close together.